Matter appears solid only because our senses stop asking questions. Physics does not. When experiments stripped matter down to what can actually be measured, solidity vanished. Light carries energy, yet has no mass. Electrons behave as point-like states with no internal size. Protons are stable without being elementary. Gravity responds to energy itself, not to substance. These are not poetic ideas. They are experimental facts. Today, we will move through 10 connected problems that physics was forced to confront as experiments stripped matter down to what can actually be measured. How energy confined as light can increase mass without creating new particles. What mechanism allows mass to appear at all? Why nature settles on two dominant mass scales, electron and proton, rather than a smooth continuum. Why those states must carry electric charge, and why charge never escapes gravity. How electrons and protons convert into neutrons, how neutrons and protons bind further, and why that binding releases enormous energy. And finally, how all of this works even when particles have no internal structure. We begin at the point where familiar explanations stop working. Part 1. Why a photon, or its mathematical structure, could ever become a stable state with mass. Light has no rest mass. This is not a philosophical statement, but one of the most tightly tested facts in physics. Every precision experiment, from early electromagnetic measurements to modern accelerator constraints, agrees that a free photon has no rest frame and no intrinsic mass. And yet, light undeniably carries energy, momentum, and stress. It exerts pressure, bends spacetime, and contributes to gravity. This combination creates a structural tension at the heart of physics. If mass is a form of energy, and light is pure energy, under what conditions, if any, can light contribute to something that behaves like mass? This question is not speculative. It arises directly from how mass is defined operationally. In both special and general relativity, mass is not a substance, but a bookkeeping of energy that cannot be transformed away. Whenever energy is confined, constrained, or forced into a persistent configuration, it contributes to the inertial and gravitational mass of the system. The issue is not whether light can be associated with mass in some sense, it clearly can, but whether it can do so in a way that produces stable, particle-like states, rather than transient effects. The first and most conservative framework in which this happens is often summarized as the confined photon scenario. Consider a perfectly reflective cavity, or more realistically, a high-quality electromagnetic resonator. When photons enter such a cavity, they do not propagate freely to infinity. Instead, they are repeatedly reflected, forming standing wave modes. The total energy stored in these modes increases the system's energy budget. According to relativistic mass-energy equivalence, this added energy increases the total mass of the system by an amount delta equals delta E divided by c squared. Crucially, this mass does not belong to the photon as an isolated object. It belongs to the system as a whole. The cavity plus trapped radiation has greater inertia than the empty cavity. This effect is not hypothetical. It appears explicitly in the stress-energy tensor of the electromagnetic field, which is the quantity that sources gravity in Einstein's field equations. In principle, if one could weigh the cavity with sufficient precision before and after injecting electromagnetic energy, the mass difference would be measurable. In practice, such measurements are extraordinarily difficult. The energy scales involved are small compared to everyday masses, and isolating the system from environmental noise is a formidable challenge. Nonetheless, related effects are routinely observed. Changes in resonant frequency, radiation pressure forces, and inertial responses of electromagnetic systems are all consistent with the prediction that confined electromagnetic energy contributes to mass. Experiments using superconducting microwave cavities, optomechanical resonators, and ultra-stable oscillators operate within precisely this framework. What this scenario establishes is narrow but solid. Light can contribute to mass at the level of a composite system. It explains why heated objects weigh slightly more than cold ones, why energy stored in fields affects inertia, and why gravity couples to radiation. But it also draws a sharp boundary. No new particle is created. No discrete rest mass emerges. The photon remains massless. and the mass increase disappears as soon as the energy is released. This mechanism cannot explain the existence of stable elementary particles like electrons or protons. To move beyond system mass, one must confront gravity itself. In general relativity, energy curves spacetime, and curved spacetime redirects energy. This mutual interaction raises a more radical possibility. Could electromagnetic energy curve spacetime strongly enough to trap itself, forming a self-sustaining configuration with an effective rest mass? This idea was explored in the mid-20th century by John Archibald Wheeler under the name GEN, short for gravitational electromagnetic entity. A GEN is not a particle in the traditional sense. It is a localized bundle of electromagnetic radiation whose own gravitational field confines it. The electromagnetic field generates curvature. The curvature bends the trajectories of the electromagnetic field lines. The resulting configuration persists as a coherent object. In this picture, mass arises not from matter, but from the self-interaction between energy and space-time geometry. The gene has an effective rest energy, the minimum energy required to sustain the configuration, and therefore an effective mass. No additional substance is introduced. Only fields and geometry are involved. Mathematically, genes are legitimate solutions of Einstein's equations coupled to the electromagnetic field. Physically, however, they face severe challenges. The energy density required to produce sufficient curvature is enormous. Most geon solutions are unstable, slowly leaking energy through radiation or dispersing under perturbations. Over time, they decay. This instability is not a technical detail. It is a structural consequence of how electromagnetic fields behave under gravity. Observationally, if genes existed in significant numbers, they would behave as objects that interact gravitationally and electromagnetically, but lack the signatures of ordinary matter. They would not participate in nuclear reactions, chemistry, or known particle interactions. Astrophysical surveys, ranging from gravitational lensing to cosmic microwave background measurements by ESA missions, have not revealed evidence for such entities. While the idea remains conceptually important, it does not currently account for the stable matter observed in the universe. The failure of both confined photons and geons to produce particle-like stability leads to a deeper line of inquiry. Perhaps particles are not things at all, but stable configurations of underlying fields. This brings us to the third and most structurally ambitious framework, solitons and topological configurations. In many nonlinear field theories, there exist localized solutions that do not disperse. These solitons arise not because energy is trapped by walls or gravity, but because the equations themselves admit stable minima that cannot be continuously deformed into the vacuum. The stability is often topological. The configuration is characterized by an invariant that prevents it from unwinding without crossing an energy barrier. In such systems, mass emerges as the minimum energy required to maintain the configuration. This energy does not depend on motion, and therefore behaves exactly like rest mass. Importantly, solitons can exhibit particle-like properties, finite size, quantized charge, and discrete excitation spectra. Applying this idea to fundamental physics suggests a radical reinterpretation. Instead of viewing electrons, protons, or other particles as point-like objects with intrinsic properties, one can attempt to describe them as stable field configurations of a deeper underlying theory. In this framework, the photon is typically a linear excitation, a freely propagating wave, while massive particles correspond to nonlinear, self-stabilizing configurations. This distinction is critical. Linear waves superpose and disperse. Non-linear configurations can lock energy into localized structures. To convert something photon-like into something particle-like, the underlying theory must allow nonlinearities or topological constraints that prevent dispersion. Standard quantum electrodynamics does not provide such mechanisms. Its equations are linear in the photon field, and no soliton solutions exist. However, in theories beyond QED, non-abelian gauge theories, effective field theories with symmetry breaking, or speculative quantum gravity frameworks, nonlinear structures are common. The proton itself is already an example. Its mass arises primarily from the energy stored in the strong interaction fields that bind quarks together, not from the bare masses of the quarks. This fact, established through deep inelastic scattering experiments in the late 20th century, demonstrates that mass can emerge dynamically from field energy. If particles are solitonic configurations, then they should leave measurable signatures. Such configurations typically predict finite effective size, deviations from point particle form factors at high momentum transfer, and excited states corresponding to deformations of the soliton. High-energy scattering experiments at facilities like CERN place stringent limits on these possibilities. To date, electrons appear point-like, down to extremely small length scales, while protons clearly exhibit internal structure, consistent with quantum chromodynamics. This does not rule out solitonic interpretations entirely, but it confines them to energy scales far beyond current experimental reach. Any underlying field responsible for such structures must operate at energies where known symmetries and interactions merge into something deeper. Taken together, these three frameworks establish the landscape clearly. Light can contribute to mass when confined, but only as part of a larger system. Electromagnetic energy can, in principle, gravitate and self-interact, but not stably under known conditions. And stable particle-like mass most plausibly arises from nonlinear field configurations governed by symmetries and conservation laws, deeper than those of electromagnetism alone. There is no simple geometric deformation of a photon within standard physics that turns it into an electron or a proton. This is not a failure of imagination, but a consequence of equations tested to extraordinary precision. The absence of such a mechanism is itself a powerful constraint on any theory that claims to explain the origin of mass. As physicist Steven Weinberg once remarked, the more the universe seems comprehensible, the more it also seems pointless. In this context, comprehensibility comes from limits. The fact that photons resist becoming massive particles tells us something precise about the structure of physical law, and it forces the inquiry forward. If mass does not arise from bending light alone, from there, the next question follows. What mechanism does allow mass to appear at all? And why does nature select only certain stable mass scales instead of an unlimited continuum? That transition is where the structure of matter begins to reveal its deeper constraints. Part 2. If those hypotheses were true, what physical mechanism would actually explain the appearance of mass? Mass does not appear because something becomes solid. It appears because energy becomes unavoidable. This is the starting point that modern physics cannot escape. In every framework that has survived experimental testing, from special relativity to quantum field theory to general relativity, mass is never introduced as a primitive ingredient. It is always derived. It is the operational measure of energy that cannot be transformed away, removed, or allowed to disperse freely. If energy can leave a system without resistance, there is no rest mass. If energy is forced to remain, mass follows with mathematical inevitability. With that definition fixed, the three hypotheses introduced earlier are no longer abstract ideas. They become three distinct mechanisms, each answering the same question in a different way. What prevents energy from disappearing? The first mechanism is the most conservative and the most firmly grounded in existing experiments: electromagnetic energy that is confined within a system. A free photon does not rest. It propagates at the invariant speed set by spacetime itself. Because it has no rest frame, no observer can assign it a rest mass. This is not a convention. It is enforced by Lorentz symmetry and confirmed by every precision test of electromagnetism and particle physics. But confinement breaks that freedom. When photons are trapped inside a cavity, whether a mirrored enclosure, a microwave resonator, or a superconducting loop, their energy can no longer be removed by a change of reference frame. The system now contains an irreducible amount of energy. To eliminate that energy, the physical structure of the cavity must be altered. As long as the structure exists, the energy exists. In general relativity, this is sufficient to produce mass. The electromagnetic field contributes directly to the stress-energy tensor. The stress-energy tensor sources space-time curvature. The system's inertial response changes. Its gravitational influence changes. The increase in mass is exactly equal to the trapped energy divided by the square of the speed of light. This mechanism is not speculative. It is already embedded in precision physics. Stored electromagnetic energy alters the inertia of systems. Charged capacitors have greater mass than uncharged ones. Superconducting rings carrying persistent currents contribute to gravitational mass. These effects are small, but they are consistent and unavoidable. Space agencies such as NASA and ESA routinely account for stored energy when modeling spacecraft, resonators, and ultra-sensitive instruments. Even tiny discrepancies in energy accounting can lead to measurable deviations over long timescales. In this sense, mass is simply energy that has lost its freedom to leave. But the limitation is equally clear. The mass does not belong to the photon. It belongs to the system. There is no discrete rest mass spectrum. No stable particle emerges. The moment the energy is released, the mass disappears. This mechanism explains system mass, not particle mass. It explains why light contributes to weight, but not why electrons or protons exist. To move beyond this limitation, energy must not only be confined by external boundaries, it must be confined by its own influence. This leads to the second mechanism, electromagnetic energy held together by its own gravitational field. In Einstein's theory, energy does not merely respond to space-time curvature, it generates it. An electromagnetic field carries energy and momentum. That energy and momentum curve space-time. Curved space-time alters the paths along which electromagnetic waves propagate. This mutual interaction opens the possibility of a self-sustaining configuration. The logic is strict and sequential. Electromagnetic fields carry energy, momentum. Energy, momentum curve spacetime. Curved spacetime redirects electromagnetic propagation. Redirection prevents unrestricted dispersion. If these effects balance precisely, a localized configuration forms that does not require external confinement. Such a configuration possesses a minimum energy that cannot be removed without destroying the structure. That minimum energy behaves as rest energy. Divided by the square of the speed of light, it defines an effective mass. John Archibald Wheeler explored this possibility in depth and introduced the term gyeon to describe such entities. A gyeon is not a particle in the conventional sense. It has no material core. It is a knot of field energy held together by geometry. The appeal of this idea is that it derives mass entirely from fields and spacetime, with no additional assumptions. In Wheeler's formulation, matter is replaced by structure. As he famously summarized, spacetime tells matter how to move, matter tells spacetime how to curve. In a gyeon, matter is nothing but curved spacetime interacting with field energy. However, nature imposes a severe constraint. The energy density required for self-trapping is extreme. Small perturbations destabilize the configuration. Most gyeon solutions slowly radiate energy and decay. Their lifetimes depend sensitively on symmetry and idealized conditions. In realistic environments, they tend to disperse. From an observational perspective, such objects would interact gravitationally and electromagnetically, but would not participate in nuclear reactions, chemistry, or known particle interactions. Large-scale surveys, gravitational lensing maps, cosmic microwave background measurements from ESA missions, and precision cosmology place strong limits on exotic matter components of this type. As a result, gyeons remain mathematically consistent but physically unconfirmed. They demonstrate that mass can arise from energy interacting with geometry alone, but they do not account for the stable matter observed throughout the universe. This pushes the inquiry deeper, toward a mechanism that does not rely on external confinement or delicate gravitational balance. The third mechanism treats mass as an intrinsic feature of stable field configurations, rather than as a property added afterward. This is the domain of solitons and topological configurations. In many nonlinear field theories, there exist localized solutions that do not spread out over time. These solutions are not confined by walls or gravity. They persist because the structure of the equations forbids them from decaying continuously into the vacuum. Their stability is guaranteed by topology or by nonlinear dynamics. The key requirement is that the field equations admit multiple inequivalent configurations separated by energy barriers. Once a configuration forms, it cannot be removed without supplying enough energy to cross the barrier. The minimum energy required to sustain the configuration is fixed. It does not depend on motion. It behaves exactly like rest mass. In this framework, mass is not attached to an object. It is the energy cost of existence for a particular configuration. This idea is not foreign to established physics. The proton provides a concrete example. Its mass is not dominated by the bare masses of its constituent quarks. Instead, it arises primarily from the energy stored in the strong interaction fields that bind quarks together. This was established through deep inelastic scattering experiments at SLAC and later confirmed at CERN. The majority of the proton's mass is field energy. Soliton-based interpretations generalize this logic. They suggest that stable particles may be configurations of deeper fields, stabilized by symmetry and topology rather than by material substructure. In such models, intrinsic properties, mass, charge, and interaction behavior emerge from how the configuration fits within the field's allowed states. These configurations are not arbitrary. They carry distinct signatures, finite size, characteristic excitation spectra, deviations from idealized point behavior at high momentum transfer. This is why modern accelerators probe smaller and smaller length scales. So far, electrons appear point-like down to extremely small distances, while composite particles reveal internal structure consistent with quantum chromodynamics. The absence of observed solitonic signatures at accessible energies does not invalidate the mechanism. It constrains the scale at which it could operate. If such configurations exist, they belong to a deeper layer of physics beyond current experimental reach. Among the three mechanisms, this third one stands apart. It is the only framework capable of producing stable particles with discrete rest masses and intrinsic properties. It does not rely on external boundaries. It does not depend on finely balanced gravitational self-interaction. It derives mass from necessity rather than attachment. This distinction is decisive. The first mechanism produces mass that is collective and temporary. The second produces mass that is conditional and often unstable. The third produces mass as an intrinsic feature of a stable configuration. None of these mechanisms contradict existing data, but they cannot be freely mixed. Each carries strict constraints imposed by symmetry, conservation laws, and observation. As Carl Sagan once remarked, science is a way of thinking much more than it is a body of knowledge. Here, that way of thinking demands restraint. Any mechanism that explains mass must also explain why mass is rare, why stable particles occupy narrow ranges, and why most conceivable configurations never exist. If mass were easy to produce, the universe would be filled with stable configurations of every possible energy. Chemistry would fail. Structures would collapse into chaos. The fact that matter is sparse, structured, and selective tells us that stability is not generous, it is restrictive. And that restriction points forward. If mass appears only when energy is confined into specific, non-escapable configurations, then a further question follows. Part 3. Why does nature settle on two dominant mass scales, the electron and the proton, rather than an infinite continuum? If mass were merely a numerical label attached to energy, nature would have no reason to stop at two dominant values. Every slight variation in configuration would survive. Mass would come in a smooth spectrum. Matter would exist at all scales with equal legitimacy. But this is not what experiments reveal. Instead, ordinary matter is built almost entirely on two mass scales, the electron and the proton. Everything else is either unstable, short-lived, or requires extreme conditions to exist at all. This outcome is not accidental. It is the inevitable consequence of how stability works in field theories governed by symmetry, dynamics, and energy ordering. The central statement of this part is precise. Only configurations that simultaneously satisfy symmetry constraints, dynamical self-consistency, and absolute energetic stability can persist. Almost all conceivable configurations fail at least one of these requirements and disappear. To understand why this leaves so few survivors, each layer of constraint must be examined carefully. The first layer is the most easily misunderstood. Stability is not something that configurations are allowed to have. It is something they must be forced into by constraint. In physics, a configuration does not persist simply because the equations permit its existence. Persistence requires that there be no available path, continuous or discrete, by which the configuration can lose energy while respecting conservation laws. If such a path exists, the configuration will follow it. There is no hesitation, no delay, and no exception. For a configuration to be stable, 3 conditions must be satisfied simultaneously. First, it must not be able to radiate its energy freely. Any configuration that can shed energy continuously through waves, particles, or field excitations will do so until it vanishes or transforms. Second, it must respect the fundamental symmetries of the theory. Symmetries are not aesthetic preferences, they enforce conservation laws. Violating a symmetry removes the protection that prevents decay. Third, it must not have access to a lower energy configuration with the same conserved quantum numbers. If such a configuration exists, decay is inevitable. Most imagined configurations fail immediately. Some violate symmetry. Some have obvious radiation channels. Others are metastable at best, disappearing as soon as perturbations appear. Stability is therefore not common. It is exceptional. This immediately rules out the idea of a continuous mass spectrum of stable matter. A continuum would imply configurations arbitrarily close in energy, connected by smooth paths. Smooth paths allow decay. Stability requires isolation. The second layer introduces the decisive role of symmetry and quantization. In the frameworks discussed earlier, especially those involving solitons or topological configurations, the space of possible field states is not continuous. It is partitioned into distinct sectors by symmetry and topology. These sectors are not connected by smooth transformations. Moving from one sector to another requires violating a conservation law or crossing an energy barrier. This partitioning is not imposed artificially. It arises directly from the mathematical structure of the fields. Gauge symmetries, global symmetries, and topological constraints divide configuration space into discrete classes. Within each class, the system seeks the lowest energy configuration. That configuration is stable, not because it is preferred, but because it has nowhere else to go without breaking the rules of the theory. These lowest energy configurations appear as isolated minima in configuration space. They are discrete, they are not adjustable. Their energies, and therefore their masses, are fixed by the structure of the theory itself. From this perspective, the electron and the proton are not selected arbitrarily. They correspond to deep isolated minima in the configuration landscape. They are not representatives of a smooth family. They are endpoints. Between two such minima lies a region of higher energy. Regions of higher energy do not support rest states. They drain toward the nearest minimum. This is why intermediate masses do not persist. The third layer addresses a question that often goes unspoken. Why are there not infinitely many such minima? In principle, a complicated theory could admit many stable configurations, but physics does not merely allow structures. It constrains them aggressively. Suppose, hypothetically, that configuration space contained an infinite number of stable minima. Each minimum would correspond to a stable particle. The universe would then be filled with stable, massive states of every conceivable kind. Matter would fragment endlessly. Energy would become trapped in countless configurations. There would be no clean separation between scales. The consequences would be catastrophic for structure. Atomic organization would fail. Chemistry would not converge. Stars would not regulate fusion. Large-scale order would be impossible. None of this is observed. What experiments actually show is the opposite. High-energy collisions produce vast numbers of possible configurations. Almost all of them decay almost immediately. Resonances appear briefly and vanish. Exotic states require extreme conditions and disappear as soon as those conditions relax. This empirical fact tells us something fundamental. Configuration space is filtered with extraordinary severity. Only configurations that satisfy all constraints simultaneously survive. The overlap of all constraints is extremely small. Stability is not merely rare, it is aggressively suppressed. Within this filtered landscape, The electron and the proton occupy a special role, not because they are simple, but because they are terminal. In the language of field dynamics, they function as fixed points. A fixed point is not a state where nothing happens. It is a state from which no energetically allowed path leads downward while preserving the required symmetries and conserved quantities. The electron is such a state. It carries conserved quantum numbers, electric charge, and lepton number that forbid decay into lighter configurations. There is no lower energy state with the same quantum numbers available within known physics. It cannot be subdivided into smaller components without violating symmetry constraints. As a result, once formed, it persists indefinitely. The proton is a fixed point of a different kind. It is not elementary, but it is dynamically locked. The strong interaction confines its internal degrees of freedom so tightly that any attempt at decay would either increase energy or violate conservation laws. Within experimentally confirmed physics, there is no energetically accessible decay channel for an isolated proton. This is not a coincidence. Both particles sit at the bottom of their respective stability basins. There is no slope beneath them. Everything else slides. This understanding reverses a common intuition about nature. It is tempting to think that electrons and protons exist because they were somehow chosen. The reality is more severe. Everything else is rejected. Configurations that can lose energy do so. Configurations that violate symmetry never form. Configurations with lower energy alternatives decay. After this relentless elimination process, only a few configurations remain. Electron and proton are not special because they are favored. They are special because they are unavoidable once the rules are enforced. This elimination process operates continuously. In the early universe, extreme energies populated configuration space densely. As the universe cooled, unstable configurations disappeared. In modern accelerators, the same process repeats on small scales. Many states are created. Almost all vanish. What remains are the configurations that cannot escape. This also explains why the electron and proton mass scales are sharply defined rather than spread out. If stability depended on a single condition, many masses might survive. But stability depends on several independent constraints acting simultaneously. Each constraint removes large regions of configuration space. Only their intersection supports rest states. Where the intersection exists, mass appears. Where it does not, nothing lasts. The electron mass and proton mass are therefore not arbitrary numbers awaiting explanation by fine-tuning. They are indicators of where stability is possible at all. This connects directly to what we established earlier. In Part 1, it was shown that deforming light alone cannot produce stable matter. In Part 2, it was shown that mass appears only when energy is forced into unavoidable configurations. Part 3 now shows why such configurations are extremely rare. Nature does not permit infinitely many stable masses because doing so would destroy its own consistency. Stability is not generous. It is restrictive. And once only a few stable configurations exist, everything else, electric charge, interaction, binding, must arise as consequences of how those configurations interact with fields and with each other. That logical necessity sets the stage for the next step, understanding why these surviving configurations must carry electric charge at all and why interaction is not optional once stability is achieved. That is where the structure tightens further. Part 4. Why do stable configurations carry electric charge? A configuration that persists in nature cannot exist as an isolated mathematical curiosity. The moment it lasts longer than a fleeting fluctuation, it must coexist with surrounding fields, remain identifiable under transformations, and obey the same symmetries that govern every verified interaction. Electric charge appears precisely at this point. It is not added after stability is achieved, and it is not an optional decoration. It is the unavoidable outcome of requiring a stable configuration to exist consistently within a universe structured by gauge fields and symmetry constraints. In the framework developed so far, electrons and protons are treated as stable configurations of underlying fields. They are not mechanical objects assembled from smaller parts. Their defining feature is not composition, but persistence. Persistence, however, is not free. It is paid for by strict conditions that leave very little room for freedom. To persist, a configuration must remain dynamically stable. It must not shed energy through any available lower energy channel. It must remain well defined under changes of reference frame. And it must interact with its environment without violating conservation laws. These conditions are enforced not by interpretation, but by experimental evidence collected across atomic physics, quantum electrodynamics, and high-energy scattering. Within this landscape, electric charge emerges as a structural necessity. A stable configuration cannot remain indifferent to its surroundings. Fields are not optional features of space. They are the medium through which all known interactions propagate. Electromagnetic fields, in particular, permeate space at every scale, from atomic distances to interstellar regions. Any configuration that exists within this field must respond to it in a consistent and reproducible way. That response cannot be arbitrary. If a configuration reacted differently depending on local description or coordinate choice, its behavior would contradict the invariance principles that make physical laws predictive. Such inconsistency would immediately destabilize the configuration, allowing it to decay or dissolve. Electric charge is the rule that governs this response. It defines how a configuration transforms when the electromagnetic field is locally adjusted. It ensures that physical descriptions remain invariant, even as mathematical representations change. In technical terms, charge specifies how a configuration transforms under local gauge symmetry. Without such a specification, interaction becomes ambiguous, and ambiguity is incompatible with stability. This is why charge is not something that appears after a configuration forms. It is embedded in the conditions that allow formation in the first place. Consider what would happen if a configuration lacked electric charge entirely. It would not respond to electromagnetic fields. It would not emit or absorb photons. It would leave no trace in detectors that rely on electromagnetic interaction, which includes nearly all instruments used in experimental physics. More importantly, such a configuration would be unable to maintain a consistent identity. Without interaction, there is no operational way to distinguish it from the vacuum. In physics, indistinguishability from the vacuum is not a philosophical issue. It is a statement about measurement. If no interaction reveals the presence of a configuration, then no experiment can confirm its existence as a separate entity. Electric charge marks the threshold at which a configuration becomes physically distinguishable. This does not mean every configuration must carry electromagnetic charge. Neutral composite systems exist, but their neutrality arises from the cancellation of internal charges, not from the absence of interaction altogether. At the fundamental level, the building blocks that define those composites must still obey charge-related transformation rules. The discrete nature of electric charge follows directly from the same constraints. Stability requires the absence of nearby lower energy states. If charge varied continuously, configurations could shift gradually between interaction behaviors, always finding a slightly more favorable configuration. Such continuous drift would eliminate stability. Instead, symmetry partitions configuration space into distinct sectors. Each sector corresponds to a specific transformation rule under electromagnetic symmetry. A configuration belongs entirely to one sector or another. Crossing between sectors is not a smooth process. It requires processes that violate charge conservation, and such processes are not observed. This structure explains why electrons and protons carry charges of equal magnitude and opposite sign. They occupy distinct symmetry sectors that cannot be connected by continuous deformation. Their charges are not numerical coincidences. They are labels that identify which sector each configuration inhabits. This picture is not speculative. Charge quantization has been confirmed with extreme precision, from early 20th century experiments to modern collider data. No deviation from discrete values has been observed, even at energy scales explored by contemporary particle accelerators. The necessity of charge becomes even clearer when stability is examined dynamically. A stable configuration must not only resist decay, it must also resist deformation under interaction. Electromagnetic fields fluctuate constantly. A configuration that interacts inconsistently with those fluctuations will experience forces that disrupt its internal balance. Charge defines how such forces act. It determines the direction and magnitude of interaction in a way that preserves internal consistency. Without charge, or with ill-defined charge, electromagnetic fluctuations would act unpredictably, introducing instability rather than interaction. This is why charge is better understood as a rule of engagement rather than a substance. It does not describe what a configuration is made of. It describes how it participates in the shared structure of physical law. The electron provides a clear example. It exhibits no internal structure down to the smallest scales probed by experiment. Its stability is absolute within current observational limits. That stability depends on the strict conservation of its charge. No process has ever been observed that allows an isolated electron to lose or alter its charge without violating established symmetries. This conservation is not an arbitrary rule imposed by theory. It is a direct consequence of the transformation properties required for consistent interaction. If an electron could change its charge continuously, its interaction with the electromagnetic field would lose coherence, leading to decay channels that are not observed. The proton presents a different case. It is not elementary, yet it is stable on cosmological timescales. Its charge reflects the net transformation behavior of its internal configuration. While its constituents carry fractional charges, the proton as a whole occupies a well-defined symmetry sector. This sector assignment is what allows it to interact consistently with electrons, form atoms, and participate in chemistry. In both cases, charge is not the cause of stability. It is the condition that makes stability possible. Another important consequence follows. Charge cannot be removed without consequence. A hypothetical configuration, identical to an electron in every respect, except charge, would not behave like an electron. It would not bind to protons. It would not participate in atomic structure. And without electromagnetic interaction, it would not remain localized. Such a configuration would lack the mechanisms required to maintain coherence in an environment dominated by fluctuating fields. Its absence from observation is not surprising. It is expected. This reasoning explains why stable configurations that participate in matter must carry charge. Neutrality is allowed only at the composite level, where internal charges balance while preserving interaction channels at smaller scales. The emergence of charge also clarifies why it cannot be neutralized in the same way as mass or energy. Electric charges can cancel, but the rules governing charge remain. A neutral atom still interacts electromagnetically through polarization and higher-order effects. Complete isolation is never achieved. This persistent interaction ensures that configurations remain embedded in the network of physical law. It prevents the formation of disconnected, unobservable entities that would undermine the predictive power of physics. Historically, this understanding emerged gradually. Early models treated charge as a substance or fluid. Later developments, particularly in gauge theory, revealed charge as a manifestation of symmetry. The work of Hermann Weyl, followed by developments in quantum electrodynamics, demonstrated that charge conservation is inseparable from the structure of electromagnetic interaction itself. Modern experiments reinforce this picture. Precision measurements of charge conservation, tests of gauge invariance, and studies of particle interactions at high energies all support the view that charge is not optional. It is built into the framework that allows stable configurations to exist at all. At this stage, a clearer pattern had formed. Mass represents the energetic cost required for a configuration to persist. Charge represents the rule that allows persistence to remain consistent under interaction. Neither arises from hidden components. Both arise from constraint. Energy and charge together bring the configuration into a broader interaction framework. Energy, regardless of form, affects the geometry of space-time. Unlike charge, this effect cannot be screened or cancelled. Every configuration that exists must therefore influence and respond to gravity. This transition is not a change of topic. It is the next consequence enforced by the same logic that introduced charge. Stability, interaction, and symmetry do not stop at electromagnetism. They extend into space-time itself. And that extension leads to the next question. Part 5. Why do those configurations interact gravitationally? The most unsettling fact about gravity is not its weakness, but its inevitability. You can shield electric charge, you can neutralize it, you can arrange matter so electromagnetic forces cancel almost perfectly. Yet no experiment, from laboratory scales to deep space observation, has ever revealed a way to hide from gravity. The reason is not mysterious once the structure of stable configurations is taken seriously. Any configuration that exists stably must carry energy, and energy does not merely sit inside space. It reshapes space and time themselves. That reshaping is what we call gravity. In the path we have followed so far, mass appeared as the energetic cost of persistence. Electric charge emerged as the rule that allows persistence to remain consistent under interaction. Gravity now enters not as an additional property, but as a consequence that cannot be avoided once energy is present at all. This is not a philosophical statement. It is a result encoded directly in the equations that have survived every experimental test of gravity to date. At first glance, gravity appears similar to other interactions. Objects attract each other. Forces act at a distance. But this resemblance dissolves when the mechanism is examined carefully. Electric forces depend on charge. Strong forces depend on color charge. Weak interactions depend on particle type. Gravity depends on none of these. It responds only to energy and momentum, regardless of how that energy is packaged. This distinction matters. An electron and a proton interact electromagnetically in opposite ways because their charges differ, but gravitationally, they behave almost identically once their energies are accounted for. A neutral atom, despite having zero net electric charge, still contributes to gravitational attraction. Even radiation, photons with no rest mass, follows curved trajectories in gravitational fields. The underlying reason is simple and severe. Gravity does not see charge. It sees the stress, energy content of a configuration. If energy cannot be eliminated, gravity cannot be avoided. This principle was made explicit in the early 20th century when Einstein replaced the idea of gravity as a force with a geometric description. In general relativity, energy and momentum determine how space-time curves, and that curvature determines how objects move. The field equations do not ask whether the energy comes from mass, electromagnetic fields, pressure, or radiation. They treat all contributions equally. This universality has been tested repeatedly. Observations of gravitational lensing show that light bends near massive objects, despite carrying no rest mass. Measurements of binary pulsars confirm that electromagnetic energy stored in fields contributes to gravitational mass. Satellite experiments verify that objects with different compositions fall identically in Earth's gravitational field to extremely high precision. These results leave no room for selective coupling. Gravity couples to everything that carries energy. A stable configuration, by definition, cannot rid itself of energy without ceasing to exist. The interaction is therefore unavoidable. Electric charge might seem at first like a candidate for exemption. After all, charge can cancel. A positive charge surrounded by an equal negative charge produces no external electric field. But cancellation is a property of electromagnetic interaction, not of energy itself. In the framework developed earlier, charge is not an add-on. It is inseparable from the configuration's interaction with the electromagnetic field. That interaction requires energy. The field surrounding a charged configuration stores energy. The configuration's internal dynamics store energy. Even when charges cancel externally, the energy that made cancellation possible remains. That energy still contributes to space-time curvature. This is why there is no such thing as non-gravitating charge. A charged configuration always carries electromagnetic field energy. That energy enters the gravitational field equations on equal footing with all other forms of energy. The equations do not allow exceptions. This leads to a crucial clarification. Gravity is not an extra force layered on top of existing interactions. It is the response of space-time itself to the presence of energy. When a stable configuration exists, space-time cannot remain flat around it unless the energy is exactly zero. Exact zero energy configurations cannot persist. Therefore, curvature follows existence. This perspective resolves a common confusion. One might ask why gravity is so weak compared to electromagnetism. The answer lies in what is being compared. Electromagnetism acts between charges. Gravity acts between energy densities. For most particles, the energy scale associated with charge interactions dwarfs the energy scale associated with space-time curvature at laboratory distances, but weakness does not imply optionality. Gravity acts everywhere, all the time, on everything. The bending of light near stars, first confirmed during the solar eclipse of 1919, illustrates this point. Photons experience no force in the classical sense. Yet their paths curve, because space-time itself is curved. Gravity influences motion by shaping the geometry through which motion occurs. Another striking feature emerges at this stage. Gravity always attracts. Unlike electromagnetism, it never repels. This is not a coincidence, and it is not a mere empirical rule. It follows directly from how energy enters the structure of space-time. Electric charge comes in positive and negative forms. Fields can cancel. Energy does not behave this way in stable configurations. While certain theoretical constructs allow for negative energy densities in limited contexts, stable configurations that persist in nature do not permit complete cancellation of energy. The total energy associated with a stable configuration remains positive. As a result, the curvature produced by energy has a consistent sign. That curvature leads to trajectories that converge rather than diverge at large scales. This is why gravitational attraction dominates cosmological structure formation, from galaxies to clusters to the large-scale web mapped by modern telescopes. The fact that gravity only attracts is not an added rule. It is a consequence of energy positivity combined with space-time geometry. The impossibility of gravitational shielding follows from the same logic. Electric fields can be blocked by conductors. Magnetic fields can be redirected. No known material can block gravity. The reason is not technological limitation. It is conceptual necessity. Shielding would require removing or cancelling energy, but stable configurations cannot shed all energy without ceasing to exist. Even composite systems with zero net charge and minimal interaction still possess rest energy. That energy shapes spacetime. The curvature persists. Experiments designed to detect deviations from this behavior have consistently failed to find any. Precision tests of the equivalence principle show that all forms of matter and energy fall in the same way. Observations from space-based missions confirm that gravitational mass and inertial mass are indistinguishable to extraordinary accuracy. These results are not isolated facts. They are interconnected consequences of a single requirement. Stability demands energy, and energy demands geometry. Historical development reinforces this picture. Before general relativity, gravity was treated as a force acting instantaneously at a distance. That model struggled to incorporate energy from fields and radiation. Einstein's framework resolved these inconsistencies by redefining gravity as geometry. Later discoveries deepened this understanding. The realization that pressure and stress contribute to gravitational mass, confirmed in astrophysical contexts, demonstrated that gravity responds to the full energy, momentum content of configurations. This includes contributions from electromagnetic fields, nuclear binding energy, and even vacuum energy. Modern cosmology depends on this universality. Models of stellar evolution rely on gravitational effects of radiation pressure. Black hole physics depends on the gravitational role of electromagnetic and kinetic energy. Gravitational wave observations confirm that dynamic energy flows generate space-time ripples detectable across vast distances. None of these phenomena require invoking internal structure beyond energy distribution. The interaction is purely geometric. From the perspective built across these parts, gravity completes the picture of existence. Mass determines how much energy a configuration requires to persist. Charge determines how it interacts consistently with electromagnetic fields. Gravity determines how its energy reshapes the spacetime in which all interactions occur. These are not independent attributes. They are interconnected consequences of the same requirement: consistency under interaction and persistence under dynamics. From this perspective, gravity appears as a universal feature. There is no special mechanism needed to explain why charged particles gravitate. They gravitate because charge cannot exist without energy, and energy cannot exist without influencing geometry. This reasoning also clarifies why gravity cannot be turned off even in neutral systems. A neutral atom has zero net charge, but it still has mass. That mass includes contributions from binding energy, kinetic energy of constituents, and electromagnetic field energy. All of these contribute to spacetime curvature. Even systems dominated by radiation, such as early universe plasmas or photon gases, gravitate. Their energy density curves spacetime, shaping cosmic expansion and structure formation. Gravity responds to what exists, not to how existence is labeled. A structural pattern becomes easier to see here. Gravity is not something matter does. It is something spacetime does in response to matter and energy. Stable configurations do not choose to gravitate. They force spacetime to respond by existing at all. If gravity is the geometric response to energy, and energy represents the cost of stability, then the way stable configurations combine, transform, and release energy moves to the center of the picture. The next step is straightforward. When stable configurations interact strongly enough to change form, what mechanisms allow those transformations to occur without breaking the constraints that made stability possible in the first place? That is where the discussion moves next, into the processes that allow configurations like electrons and protons to reorganize into new forms, while still obeying the same constraints that made gravity inevitable in the first place. Part 6. How do an electron and a proton combine to become a neutron? If electrons and protons could merge simply because they attract each other, ordinary matter would be unstable everywhere. Hydrogen atoms would quietly collapse into neutrons. Chemistry would never form, stars would never shine, and the universe would look nothing like what we observe. The fact that this does not happen is not a minor detail. It is a strict constraint imposed by how nature allows stable configurations to transform. The conversion of an electron and a proton into a neutron is therefore one of the most revealing processes in fundamental physics, because it exposes the exact boundary between what interactions are allowed to do and what they are fundamentally incapable of doing. Within the framework developed so far, electrons, protons, and neutrons are not mechanical objects assembled from parts. They are stable configurations defined by energy, symmetry, and conservation laws. Any process that converts one such configuration into another must obey every one of those constraints simultaneously. That requirement is so severe that almost all familiar interactions are immediately excluded. The first clarification must be absolute. The process, electron plus proton neutron, is not a binding process. Nothing is being glued together. No force is pulling two intact objects into a composite. After the process completes, there is no electron and no proton left inside the neutron. The original configurations no longer exist. What occurs is a conversion from one allowed configuration of fields to another allowed configuration with different internal quantum numbers. This distinction matters because most forces in physics do not have the authority to perform such conversions. They can rearrange positions, energies, and trajectories. They cannot rewrite identity. Electromagnetism provides a clear example of this limitation. The electromagnetic interaction responds to electric charge. It accelerates charged particles, binds electrons to nuclei, and governs chemistry. Yet, in every electromagnetic process, the identity of the interacting particles is preserved. An electron remains an electron. A proton remains a proton. Charges move and energies shift, but particle types do not change. This is not a weakness of electromagnetism. It is a defining feature. The equations of quantum electrodynamics are built to conserve particle identity. There is no term in the electromagnetic interaction that allows a quark to change flavor or a lepton to disappear. Gravity is even more restricted. It responds to energy, momentum alone. It bends trajectories and shapes spacetime. It does not access internal quantum numbers at all. Gravity cannot distinguish an electron from a muon except through their masses. It therefore has no mechanism to transform one stable configuration into another. If the electron-proton conversion relied on either of these interactions, it would never occur. The only interaction that can perform this transformation is the weak interaction. This is not because it is stronger or weaker than the others, but because it is different in kind. The weak interaction is the only fundamental interaction that allows changes in particle identity while preserving conservation laws. The specific process is known as electron capture. In this process, an electron is absorbed by a proton. Inside the proton, one of its up quarks converts into a down quark. The proton's internal configuration changes. Un neutron émerge. This conversion is not arbitrary. It is governed by the weak interaction's charged current, mediated by the exchange of a W boson. That exchange permits the change of quark flavor and lepton number in a tightly regulated way. Without this interaction, the conversion is forbidden. No amount of electromagnetic attraction or gravitational compression can substitute for it. The emission of a neutrino during this process is not optional. It is required. When an electron and a proton convert into a neutron, several conservation laws must remain satisfied. Total energy must balance. Linear momentum must balance. Angular momentum, spin, must balance. Electric charge must balance. Lepton number must balance. If only a neutron were produced, these balances would fail. There would be excess spin and momentum with nowhere to go. The neutrino carries away exactly what cannot remain in the neutron, while interacting so weakly that it escapes almost undetected. This is why the neutrino was predicted long before it was observed. It was not invented to explain an anomaly. It was demanded by conservation laws. When neutrinos were finally detected, it confirmed that the weak interaction obeys those laws with extraordinary precision. In electron capture, the neutrino is not a byproduct. It is the accounting mechanism that makes the transformation possible. Another constraint must be emphasized. The process does not occur freely. A neutron is slightly more massive than a proton. Creating a neutron from a proton and an electron requires additional energy. In free space, there is no available source for that energy. As a result, an isolated electron and proton do not convert into a neutron. Electron capture becomes possible only in environments where the total energy of the system decreases after the conversion. This occurs inside certain atomic nuclei. In those nuclei, replacing a proton with a neutron can lower the overall nuclear energy because of changes in nuclear binding. The energy difference is released via the neutrino. This condition explains why electron capture is selective. Some isotopes undergo it, others do not. The process is allowed only when it leads to a more stable configuration. This selectivity is not a complication. It is evidence that the rules are being enforced consistently. The role of environment here is crucial. Stability is not an absolute property of a configuration in isolation. It is defined relative to the energy landscape in which the configuration exists. An electron and a proton are stable as separate entities in most circumstances. Inside certain nuclei, the combined configuration of a neutron becomes energetically preferred. The weak interaction provides the mechanism. The nuclear environment provides the energy incentive. Conservation laws regulate the transition. Remove any one of these elements, and the process does not occur. There is no loophole. Historical evidence supports this structure. Electron capture was first inferred from nuclear decay patterns that could not be explained by beta decay alone. Experiments showed nuclei changing charge without emitting electrons. Later measurements confirmed neutrino emission and verified the weak interaction mechanism. Astrophysical observations extend this understanding. In massive stars, electron capture plays a decisive role during core collapse. As electrons are captured by protons, electron pressure drops. Gravity gains the upper hand. The core collapses, leading to supernova explosions. The elements forged in those explosions seed future generations of stars and planets. This is not a marginal effect. It shapes cosmic evolution. From the perspective of stable configurations, electron capture demonstrates a deeper principle. Transformations are permitted only when they increase overall stability. The weak interaction does not randomly convert particles. It opens specific channels that are available only under precise conditions. This is why the universe does not dissolve into neutrons. It is why hydrogen remains stable. It is why stars burn steadily rather than collapsing instantly. The constraints are not fragile. They are enforced everywhere. It is also important to recognize what electron capture does not require. It does not require speculative internal structures beyond established quark content. It does not require hidden forces. It does not require violations of known symmetries. Everything involved in the process has been measured, tested, and confirmed across multiple domains of physics. The weak interaction, quark flavor change, neutrino emission, and energy thresholds are all part of the same experimentally verified framework. This economy of explanation is not accidental. It reflects how tightly nature restricts what transformations are allowed. At this point in the series, the logic has narrowed dramatically. Electromagnetism cannot change identity. Gravity cannot change identity. Only the weak interaction can. Electron capture is therefore not one mechanism among many. It is the only mechanism consistent with all constraints. This understanding sets the stage for the next step. Once neutrons exist alongside protons, a new problem emerges. Neutrons carry no electric charge. Protons repel each other electrically, yet atomic nuclei remain bound. The process that creates neutrons does not explain how they stay together with protons afterward. That binding occurs through an entirely different mechanism, operating at extremely short distances and governed by the residual effects of the strongest interaction in nature. Explaining nuclei requires moving beyond conversion and toward binding, beyond the weak interaction and into what remains of the strong force. That shift sets the stage for the next part. Part 7. By what mechanism can neutrons and protons continue to bind together? If neutrons and protons were governed only by the forces we meet in everyday physics, atomic nuclei would never exist. Electric forces alone would push protons apart. Gravity would be far too weak to matter at microscopic scales. And yet, inside every stable nucleus, neutrons and protons remain locked together with extraordinary persistence. The reason is neither mysterious nor accidental. It comes from a very specific remnant of a much deeper interaction, an interaction so strong at its core that even its leftovers are enough to hold matter together. Neutrons and protons bind because of the residual strong nuclear force. Not a new fundamental force, not an extra layer added by hand, but a remaining effect of the strong interaction that operates inside them. This force appears only at extremely short distances, acts independently of electric charge, and reshapes the energy landscape of matter in a decisive way. To see why this works, and why it works only under very precise conditions, we need to unfold the mechanism step by step. The first point that must remain clear is that the residual strong force is not an independent interaction invented to save nuclear stability. Protons and neutrons are not elementary particles. They are stable configurations of the strong interaction itself, bound states of quarks held together by gluons. Inside each proton or neutron, the strong interaction confines quarks so tightly that separating them would require enormous energy. That confinement is not perfectly sealed. While most of the strong interaction is locked inside the proton or neutron, a small portion extends beyond the boundary of the configuration. This extension is not a leakage of particles, but a persistence of field effects at the edges of the bound state. That persistence is what we call the residual strong force. It is analogous, in a limited sense, to how electrically neutral atoms can still attract each other through van der Waals forces. The atom as a whole is neutral, yet its internal structure leaves behind an interaction footprint. In nuclei, the effect is vastly stronger and far more consequential. This immediately explains why neutrons can bind despite carrying no electric charge. Electric forces do not govern nuclear binding, they interfere with it. A proton carries positive electric charge. A neutron does not. If electromagnetism were the primary binding mechanism, proton-neutron binding would be weak, and proton-proton binding would be impossible. Experiments show the opposite. Proton-neutron binding is the most stable configuration in light nuclei. The reason is that the residual strong force does not depend on electric charge. It depends on proximity and internal configuration, specifically spin alignment and spatial overlap of the nucleon states. When a neutron and a proton approach within about 1 femtometer, the residual strong interaction becomes dominant, overwhelming electromagnetic effects. At that distance, Electric repulsion becomes a secondary detail. The energy landscape is governed by the strong force remnant. The short range of this force is not a flaw. It is a necessity. The residual strong force falls off extremely rapidly with distance. Beyond a few femtometers, it becomes negligible. This sharp cutoff ensures that nuclear binding does not extend indefinitely. If the force were long-range like gravity, matter would collapse into a single dense object. If it were too weak, nuclei would never form. Instead, the force acts only when nucleons are nearly in contact. This creates nuclei of finite size, with well-defined boundaries and predictable structure. The force binds neighbors, not distant participants. This distance dependence has been confirmed through scattering experiments and nuclear spectroscopy. It is built into every successful nuclear model used today, from shell models to effective field theories. The distinction between proton-proton and proton-neutron binding follows naturally from this picture. When two protons approach each other, the residual strong force attempts to bind them. At the same time, the electromagnetic force pushes them apart. Whether binding occurs depends on which effect dominates. In light nuclei, the electromagnetic repulsion is significant. A proton-proton pair alone does not form a stable bound state. A neutron changes everything. It contributes residual strong attraction without adding electric repulsion. The neutron acts as a stabilizing participant, allowing the nucleus to reach a lower energy configuration. This is why stable nuclei require neutrons. As atomic number increases, more neutrons are needed to counterbalance the growing electric repulsion between protons. This balance is not aesthetic. It is enforced by energy minimization. At the deepest level, binding occurs because the combined neutron-proton configuration has lower total energy than the separated particles. This principle has appeared repeatedly throughout the series. A configuration forms only if it costs less energy to exist than the alternatives. Nuclear binding follows exactly this rule. When a neutron and a proton approach closely enough, the residual strong force reshapes their joint energy landscape. A potential well appears. If the depth of that well exceeds the kinetic energy trying to pull the particles apart, a bound state forms. The resulting configuration is not merely two particles sitting side by side. It is a new state with its own energy minimum. Escaping that minimum requires energy input. Without it, the configuration persists. This is why nuclear binding releases energy when it forms and requires energy to undo. The historical development of this understanding is worth noting. In the early 20th century, nuclear stability was deeply puzzling. Electromagnetic theory could not explain it. Gravity was clearly irrelevant. The discovery of the neutron in 1932 provided a critical clue, but not a complete answer. Only after the development of quantum chromodynamics, the theory of the strong interaction, did the picture become coherent. The realization that nucleons were composite objects, and that the strong force responsible for their internal stability could have residual effects, resolved the puzzle. Modern nuclear physics relies on this framework. It is not speculative. It underpins calculations of nuclear binding energies, reaction rates, and decay pathways used in laboratories and astrophysical models alike. This mechanism also explains why nuclear binding is selective. Not all neutron-proton combinations form stable nuclei. Spin alignment matters, relative motion matters. Quantum statistics impose restrictions. These constraints arise naturally from the underlying fields and symmetries. They do not require additional assumptions. They determine which configurations are allowed and which are forbidden. The result is a structured nuclear landscape, some combinations stable, others fleeting, many impossible. This structure is not arbitrary. It reflects the precise balance of forces and constraints acting at the femtometer scale. Astrophysical evidence reinforces this view. In stellar cores, nuclear fusion proceeds only when conditions allow nucleons to overcome electromagnetic barriers and enter the range of the residual strong force. Once they do, binding becomes energetically favorable and energy is released. Stars shine because this mechanism works exactly as described. Supernovae occur when nuclear binding can no longer stabilize matter against gravitational collapse. Neutron stars form when nuclear and gravitational effects reach a new balance. None of these phenomena require new forces. They arise entirely from the residual effects of the strong interaction and the constraints it imposes. Mass reflects the energy required to sustain a stable state. Charge governs how that state participates in electromagnetic interactions. Gravity expresses how space-time responds to the presence of energy. And residual strong binding determines whether neutrons and protons can remain locked together as a nucleus. Each layer builds on the previous ones without contradiction. No internal machinery is introduced. No extra assumptions are needed. Neutrons and protons bind not because they are pulled together by an added force, but because the universe allows, and prefers, configurations that minimize energy under the existing rules. One subtle point deserves emphasis. The residual strong force is not adjustable. Its strength and range are fixed by the underlying theory. The universe does not tune nuclear stability manually. Stability emerges automatically from the interaction structure. This is why nuclear physics is predictive rather than descriptive. Binding energies, decay modes, and reaction thresholds can be calculated and confirmed experimentally. Discrepancies are rare and informative. As this part comes together, the focus shifts forward. If neutron-proton binding produces stable nuclei, and if that binding alters the energy balance of matter, then attention turns to what follows from that change. When binding lowers the total energy of a configuration, the difference cannot remain hidden. It must be released. The form and scale of that release govern phenomena ranging from nuclear reactors to the lifetimes of stars. This shift, from the mechanism of binding to the release of energy, opens the next part, where the same configuration logic explains why nuclear processes rank among the most powerful energy sources known in the universe. Part 8. Why does the combination of a neutron and a proton release so much energy? The moment a neutron and a proton bind into a single nuclear configuration, an enormous amount of energy is released, not because energy is created, not because a force suddenly turns on, but because the system abandons a costly way of existing and settles into a configuration that demands less energy to remain real. This release is not dramatic by choice, it is compulsory. It is enforced by the accounting rules that govern every stable structure in the universe. To understand why the released energy is so large, one must first let go of a deeply ingrained intuition that binding is an act of construction. In nuclear physics, binding is not construction, it is subtraction. What matters is not what is added, but what is no longer required. Before binding, the neutron and the proton exist as two independent configurations. Each carries its own rest energy, its own internal field energy, and its own contribution to the stress energy budget of space-time. The total energy of the system is simply the sum of those two independent costs. There is no shared structure, no shared stability, and therefore no shared economy. After binding, the situation changes fundamentally. The neutron-proton pair becomes a single configuration, governed by a joint stability condition. The system no longer needs to pay twice for existence. Some of the energetic cost that was previously unavoidable becomes redundant. That redundancy must be expelled. The universe does not store surplus energy without a configuration to hold it. This is the core reason energy is released. It is essential to emphasize that nothing about this process violates conservation laws. There is no mysterious surplus. The energy released is precisely the difference between two allowed configurations, one that costs more energy to exist and one that costs less. This difference is what nuclear physics calls binding energy, but the term often misleads. Binding energy is not energy stored inside the nucleus like fuel in a container. It is the energy that the system would require to be torn back apart into its original, more expensive configuration. The fact that energy must be supplied to undo the binding is the mirror image of the fact that energy was released when the binding occurred. In the configuration-based framework we are using, binding energy is simply the numerical measure of how much cheaper the bound configuration is compared to the unbound one. Why then is this energy difference so large? The answer begins with the nature of the interaction that governs neutron-proton binding, the residual strong interaction. This interaction is not a gentle attraction that increases gradually with proximity. It is steep, short-ranged, and highly nonlinear. At distances comparable to the size of nucleons, on the order of a femtometer, the energy landscape changes abruptly. As a neutron and a proton approach each other within this range, the potential energy of the combined configuration drops rapidly. The descent is not shallow, it is sharp. A sharp descent in energy means a large difference between the initial and final states. Large differences must be released. This steepness has been measured and mapped through decades of scattering experiments. Proton-neutron cross-sections, deuteron binding measurements, and nuclear resonance studies all point to the same conclusion. The energy profile of the strong interaction at short range is extraordinarily deep. The second reason the released energy is large lies in what is being reorganized. Nuclear binding is not a rearrangement of peripheral components. It is not like chemistry, where electrons shift between orbitals while nuclei remain intact. Here, the rearrangement reaches the core of the configuration. The neutron and proton do not merely sit next to each other. Their combined state alters the allowed modes of motion, the internal energy distribution, and the effective degrees of freedom of the system. In chemical reactions, the energy landscape is shaped by electromagnetic interactions among electrons. These interactions operate at relatively low energy scales. Rearranging them yields modest energy changes. In nuclear binding, the rearrangement involves the conditions under which nucleons themselves remain stable within a joint configuration. The energy scale is correspondingly larger, millions of times larger. This difference is not incidental. It reflects the depth of the reconfiguration. In chemistry, breaking or forming a bond changes how electrons occupy available states around nuclei. The nuclei themselves are largely spectators. In nuclear binding, the nucleons are not spectators. They are participants. The configuration that defines their collective existence is altered. Because the reconfiguration is deeper, the energetic consequences are larger. A third contribution to the energy release comes from what happens after binding. Once the neutron-proton system forms a bound state, it becomes dynamically quieter. Fewer internal oscillations are allowed. Fewer decay pathways remain open. The configuration settles into a stable minimum. In energetic terms, this means that the system no longer requires continual internal motion to maintain itself. Energy that previously supported those motions is no longer needed. That energy cannot remain idle. It exits the system. This exit takes concrete, measurable forms. High-energy photons are emitted. The bound nucleus may recoil. In some cases, kinetic energy is redistributed among nearby particles. Every joule can be tracked. Experiments confirm the exact correspondence between the energy difference and the energy emitted. An important clarification follows naturally. If nuclear binding releases energy, why does it not release unlimited energy? Why does the process stop? The answer lies in saturation. The residual strong interaction does not grow indefinitely as more nucleons are added. Each nucleon interacts strongly only with a limited number of neighbors. Beyond that, adding more nucleons does not significantly deepen the energy minimum. At the same time, another effect grows steadily stronger: electromagnetic repulsion between protons. As nuclei grow larger, this repulsion increases with each additional proton. At small sizes, the strong interaction dominates. Energy is released when nucleons bind. At larger sizes, the balance shifts. Eventually, the repulsion offsets the stabilizing effect. Beyond a certain point, adding another nucleon increases the energy of the configuration instead of lowering it. This balance explains why nuclei have finite sizes and why the binding energy per nucleon peaks at intermediate mass numbers. This peak, observed near iron, is not coincidental. It is the natural outcome of competing energetic constraints. This framework also explains why energy release is selective. Not every combination of nucleons produces energy. Only those transitions that lead to a lower energy configuration are allowed to proceed spontaneously. Other transitions require energy input. Fission, fusion, and radioactive decay all obey this same logic. The direction of spontaneous change is dictated by energy economy, not by force preference. Historical developments in nuclear physics reinforce this picture. Early in the 20th century, the scale of nuclear energy release was puzzling. Classical intuitions failed. Only with the development of quantum mechanics and later quantum field theory did the underlying logic become clear. Precise mass measurements revealed that bound nuclei weigh less than the sum of their parts. This mass defect, measured in kilograms and converted via E equals mc(2), exactly matched the energy released during binding. No discrepancies were found. Later experiments refined this understanding. Nuclear spectroscopy mapped energy levels. Particle accelerators probed nucleon interactions. Each result tightened the connection between configuration stability and energy release. Astrophysical evidence confirms the same principles on a grand scale. In stellar cores, nuclear binding reactions convert higher energy configurations into lower energy ones. The released energy supports stars against gravitational collapse and powers their radiation for billions of years. Neutrino detectors, solar observatories, and stellar evolution models all rely on the same binding energy calculations. The agreement between theory and observation is not approximate. It is precise. Mass represents the energetic cost of existence. Charge represents the rule by which configurations interact consistently. Gravity represents the geometric response to energy. Nuclear binding represents the release of surplus cost when configurations reorganize more efficiently. Nothing here is decorative. Each concept follows from the same requirement. Stability must be paid for, and the universe prefers cheaper configurations whenever they are available. One subtle but crucial implication deserves attention. Because nuclear binding involves deep reconfiguration, it is rare. Barriers are high. Transitions occur only under specific conditions. When they do occur, the energy release is unmistakable. This rarity is not a limitation, it is a safeguard. Without it, matter would rearrange uncontrollably, structures would not persist. The universe would be noisy, unstable, and chemically barren. Instead, binding energy is released in discrete, regulated steps, allowing complexity to emerge. Binding explains why energy is released when nuclei form, but it does not end the story. Nuclear configurations do not remain frozen. Some decay, some split. Some reorganize into entirely new states. Each of these changes respects the same conservation rules, yet they proceed along very different routes. In some cases, energy is released. In others, energy must be supplied. The difference is not in the bookkeeping, but in how configurations evolve when stability is no longer static. To understand that, the focus must shift away from formation and toward transformation. If particles truly have no internal structure, then all of these changes must arise from the same external rules, fields, symmetries, and allowed state transitions without any hidden machinery inside. That shift brings us to the next question. Part 9. If particles have no internal structure, how can all of these phenomena still occur? At first glance, this question sounds like a contradiction severe enough to break modern physics. We speak of particles as having no internal structure, no measurable size, no inner machinery, and yet those same particles carry mass, electric charge, spin, participate in nuclear reactions, curve spacetime, and release enormous amounts of energy when configurations change. If there is nothing inside the particle, where does all of this behavior come from? The answer does not begin by redefining what is inside the particle. It begins by removing the assumption that physical behavior must originate from an interior at all. Modern physics does not treat particles as tiny mechanical objects. It treats them as states, states of fields, states constrained by symmetry, and states embedded in spacetime. Everything we observe arises from how those states are described, how they transform, and how they interact with one another through fields that fill all of space. Nothing essential is missing. Nothing is hidden behind an inaccessible internal layer. To see why this works, each layer of the idea must be examined carefully. When physicists say that an electron has no internal structure, they are not claiming that the electron is nothing. They are making a precise experimental statement. Decades of scattering experiments, ranging from early cathode ray studies to high-energy collisions in particle accelerators, have failed to reveal any substructure. No radius, no internal components, no deviation from point-like behavior down to distances smaller than 10, -19, meters. In quantum field theory, the electron is fully characterized by a set of properties: mass, charge, spin, and its transformation rules under the symmetries of spacetime and internal gauge fields. These properties are not decorations added afterward. They define what the electron is. Saying that the electron has no internal structure means that there is no additional degree of freedom inside the electron that needs to be specified to predict its behavior. Everything observable about the electron is already contained in its state description. This leads directly to the second layer. Particles are not objects in the classical sense. They are stable states of fields. In classical mechanics, an object has an interior, a surface, and parts that move relative to one another. In quantum field theory, a particle is a localized excitation of a field that satisfies certain stability conditions. The field exists everywhere. The particle is a particular way the field can exist without immediately dissolving. This distinction matters. A state can carry energy without containing smaller moving parts. A state can have momentum without internal gears. A state can interact without an internal mechanism that mediates the interaction. Consider a standing wave on a string. The wave has energy, momentum, and a well-defined frequency, yet there is no object traveling along the string. The behavior comes from the configuration of the string itself. Particles behave similarly, but in relativistic quantum fields rather than mechanical strings. In this framework, mass arises from the energy associated with maintaining the state. Charge arises from how the state transforms under gauge symmetries. Spin arises from how the state transforms under rotations in spacetime. None of these require an interior structure. This brings us to a crucial point that often goes unnoticed. Behavior in physics is determined by transformation rules, not by hidden composition. Spin is not caused by something spinning inside the particle. This was established early in the development of quantum mechanics, when it became clear that the electron's magnetic moment and angular momentum could not be explained by classical rotation without violating relativity. Instead, spin is a representation property. It describes how the electron state transforms under rotations. Electric charge is similar. It does not originate from a distribution of charge inside the particle. It arises from how the particle's state transforms under a phase symmetry of the electromagnetic field. Change the phase, and the state changes in a predictable way. That rule of transformation is what we call charge. Even interactions themselves are governed by transformation rules. When particles interact, the interaction does not occur inside either particle. It occurs in the shared field between them. The fields respond to the presence of states, and those responses alter the evolution of other states. This is why modern physics places interactions between particles rather than within them. A useful way to see this is to examine what actually happens during an interaction. When an electron attracts a proton, there is no mechanical hook or internal attraction device. The electromagnetic field adjusts to the presence of both charges. That adjustment changes the energy of the combined configuration. The particles move accordingly. When a proton and a neutron bind, there is no internal restructuring of gears. The nuclear field configuration changes. The combined state has lower energy than the separated states. Energy is released. When a particle curves spacetime, it does not push on spacetime from the inside. The energy, momentum associated with the state appears in the stress-energy tensor. Spacetime geometry responds. Other states follow the altered geometry. At no point is an internal structure required. This perspective also explains why particles can participate in reactions that seem to demand internal change. In beta decay or electron capture, the particle does not rearrange internal parts. The state changes identity because the allowed transformations under the governing symmetries permit it. For example, when an electron is absorbed by a proton to form a neutron, the process is governed by the weak interaction. A quark flavor changes. A neutrino is emitted to conserve quantum numbers. The transformation is not mechanical. It is a permitted transition between states under the rules of the weak interaction. The fact that this process can occur without any internal mechanical structure is not a weakness of the theory. It is its strength. The rules are sufficient. Another layer of this idea becomes clear when we ask what would happen if particles did have internal mechanical structure. If every particle contained smaller components with their own interactions, those components would need their own governing rules. Those rules would introduce new symmetries, new conservation laws, and new failure modes. Predictability would collapse unless the structure terminated at some level. Experimentally, no such termination has been observed. Each attempt to probe deeper has revealed not internal machinery, but simpler behavior, point-like responses governed by symmetry. This simplicity is what allows the theory to close mathematically. It is what allows conservation laws to hold exactly. It is what allows predictions to be made and confirmed to astonishing precision. In this sense, the absence of internal structure is not a limitation. It is what makes physics coherent. This coherence becomes especially important when considering conservation laws. Energy, momentum, angular momentum, and charge are conserved because the underlying symmetries are exact. These symmetries would be violated if particles had hidden internal dynamics that could exchange quantities invisibly. The fact that conservation laws work so reliably across nuclear reactions, particle collisions, and astrophysical processes strongly supports the idea that there is no hidden internal bookkeeping inside particles. Everything that matters is already visible in how states transform. From an experimental standpoint, this framework has passed every test placed before it. Precision measurements of the electron's magnetic moment match theoretical predictions to more than 10 decimal places. Scattering experiments reveal no internal size. Particle lifetimes follow symmetry-based calculations. Astrophysical observations align with predictions derived from the same field-based descriptions. Organizations such as NASA and ESA rely on these principles when modeling stellar interiors, supernovae, and the early universe. The James Webb Space Telescope interprets spectra using atomic and nuclear models that assume particles have no internal structure. These assumptions are not optional. They are built into the success of the models. There is a deeper consequence worth noting. If particles were mechanical objects with internal parts, the universe would be vastly more complicated and likely unstable. Small perturbations could excite internal modes, drain energy unpredictably, and open decay channels everywhere. Instead, particles behave as indivisible units. Their stability is protected by symmetry. Their interactions are constrained. This restraint is what allows complex structures, atoms, molecules, stars, and planets to exist for billions of years. The absence of internal structure is what makes complexity possible. By now, a pattern has emerged across the earlier parts of this series. Mass arises from the energy cost of maintaining a state. Charge arises from transformation rules under gauge symmetries. Gravity arises from spacetime's response to energy. Nuclear reactions arise from transitions between allowed configurations. None of these require an internal machine. All of them require consistency. Particles behave the way they do because the rules governing states are strict, limited, and unforgiving. Only certain states are allowed. Only certain transformations preserve the symmetries. Everything else is forbidden. This is why the world looks stable rather than chaotic. What this part leaves behind is not a final answer, but a clearer boundary. When physics describes a particle as having no internal structure, it is not claiming that explanation has ended. It is pointing to where explanation actually resides, in rules rather than in hidden components. To understand how a particle behaves, nothing needs to be opened or dissected. What matters are the symmetries it obeys, the fields it participates in, and the geometric constraints that limit how it can exist and interact. With that perspective in place, the pieces introduced across the series begin to align. If particles are understood as states, if interactions arise through shared fields, and if stability is enforced by symmetry rather than by internal machinery, then one question remains to be addressed. What determines which states are permitted to exist at all, and which are excluded? That question does not turn inward. It turns outward, toward the structure of the laws themselves. And it is there, at that level, that the series comes to rest. Part 10. How can a model with no internal structure explain mass, charge, forces, and nuclear reactions? If matter truly had no internal machinery, no hidden components, no moving parts beneath observation, then at first glance it would seem impossible for it to display such a rich range of behavior. Mass resists acceleration. Electric charge attracts and repels. Forces shape motion. Nuclear reactions release energies capable of lighting stars. In everyday thinking, such effects demand inner mechanisms. Something must be turning, pulling, or rearranging inside. And yet, every precise experiment conducted over the last century has pushed physics in the opposite direction. Again and again, nature has answered with the same result. Nothing is found inside. No sub-layers emerge. No internal clockwork reveals itself. What remains is not emptiness, but sufficiency. The behavior of matter is fully accounted for, without opening particles up at all. The reason this works is not because physics ignores the question of what matter is made of, but because it answers that question at a deeper level. Matter is not explained by listing components. It is explained by identifying which states are allowed to exist, how those states behave under symmetry, and how they interact through fields and spacetime. In this view, matter is governed by rules rather than assembled from parts. When physics describes a particle as having no internal structure, this is not a confession of ignorance. It is a deliberate descriptive choice. The statement means that no additional microscopic assumptions are required to account for all observed behavior. The electron does not need subelectrons. The proton does not need gears. Every measurable property arises from how the particle's state is defined and how that state participates in the surrounding fields. This choice is not philosophical. It is empirical. High-energy scattering experiments have tested electrons and quarks at ever smaller distance scales. If internal structure existed, it would reveal itself through deviations in scattering patterns, form factors, or unexpected resonances. None have appeared. The simplest description continues to match reality. In physics, stopping at the level that explains everything observable is not a limitation. It is precision. Within this framework, mass is the first property to be explained. Mass is often imagined as substance packed into a volume. Modern physics replaces that picture with a more exact one. Mass is the energy cost of maintaining a stable state. Any configuration that cannot rid itself of its energy without ceasing to exist carries mass. This applies equally to confined radiation, bound nuclear systems, and elementary particles. Whether energy is stored in a field configuration, trapped by boundary conditions, or locked into a stable quantum state, its persistence requires energy. Through relativity, that energy appears as mass. No inner material is required, only an unavoidable energetic commitment. This idea has been tested across domains. In nuclear physics, bound nuclei weigh less than their separated components. The missing mass precisely equals the binding energy released. In particle physics, mass values determine reaction thresholds with exact accuracy. In astrophysics, stellar evolution depends sensitively on nuclear mass differences. All of these phenomena follow from the same accounting rule. Mass measures the energy that cannot be removed without destroying the state. Electric charge is explained in an equally non-mechanical way. Charge is not something carried by a hidden component. It is a symmetry label. It tells us how a state transforms when the electromagnetic field changes. In quantum field theory, particles interact with gauge fields according to precise transformation rules. When the phase of a field shifts, charged states respond in a consistent way. That response defines charge. The value of the charge determines the strength and direction of interaction, but it does not correspond to a physical ingredient residing inside the particle. This explains why charge is discrete. Discreteness arises because symmetry classes are discrete. A state either transforms according to one representation or another. There is no continuous sliding between them without changing the identity of the state itself. Electron and proton charges differ not because of hidden composition, but because they belong to different symmetry classes. This view has extraordinary predictive power. It explains charge conservation, gauge invariance, and the exact cancellation of anomalies required for consistency. None of these rely on internal structure. They rely on mathematical symmetry that has been verified by experiment to remarkable precision. Forces, in this model, are not threads connecting particles. They are not pushes or pulls transmitted by hidden rods. They are the macroscopic description of how fields respond to states and how other states respond in turn. Electromagnetic forces arise because charged states modify the electromagnetic field around them. Other charged states evolve within that modified field. Nuclear forces arise because certain combinations of states produce lower energy configurations when brought into proximity. Gravity arises because energy and momentum alter the geometry of spacetime itself. In each case, nothing acts from inside the particle. Everything happens in the relationship between states and the fields that fill space. This relational picture eliminates the need for internal machinery while preserving every observed effect. The success of this approach is visible across scales. From atomic spectra to planetary motion, the same field-based interactions explain behavior without contradiction. Nuclear reactions provide one of the most demanding tests of any physical model. They involve profound changes in energy, identity, and stability. If any process required hidden internal components, nuclear physics would reveal them. Instead, nuclear reactions fit perfectly into the state-based description. When neutrons and protons bind, the system transitions from a higher energy configuration to a lower energy one. The difference is released as radiation, or kinetic energy. No parts are assembled, no components snap together. The system simply adopts a cheaper way of existing. When reactions reverse, energy must be supplied. When decay occurs, the system moves toward a more stable configuration permitted by conservation laws. In every case, the outcome is dictated by allowed transitions between states, not by rearrangement of internal pieces. This explains why nuclear energy is so much larger than chemical energy. Chemical reactions rearrange electronic states. Nuclear reactions alter the stability conditions of nucleons themselves. The depth of reconfiguration determines the energy involved. At this point, a deeper pattern becomes visible. The model succeeds because it focuses on what is essential and discards what is unnecessary. It does not attempt to describe what matter is made of in the everyday sense. It describes what matter is allowed to do. The key questions become: which states are permitted by symmetry, which are stable, which can interact, which can transform? Once those questions are answered, everything else follows. This approach closes the theory. It avoids infinite regress. It prevents the introduction of untestable assumptions. It yields precise predictions that can be checked by experiment. That is why modern physics adopts it. This perspective also explains why the absence of internal structure is not a gap waiting to be filled. If particles had mechanical interiors, new energy scales would appear. New decay channels would open. New conservation laws would be required. Predictability would erode. Instead, nature presents a remarkably economical design. States are simple. Rules are strict. Outcomes are constrained. Complexity arises not from complicated components, but from combinations governed by consistent laws. The fact that this economy works is not accidental. It is supported by every successful theory, from quantum electrodynamics to general relativity. Taken together, these parts point to the same underlying picture. Mass appears because energy must be paid to exist. Charge appears because interaction requires symmetry labels. Forces appear because fields mediate relationships between states. Nuclear reactions appear because some configurations are cheaper than others. None of these require internal structure. All of them require lawful behavior. This is why the model holds together so tightly. Each property reinforces the others. Remove any rule, and the structure collapses. Keep the rules, and the world becomes intelligible. The final strength of this approach lies in its humility. It does not claim to describe ultimate reality. It claims only to describe everything that can be measured, predicted, and tested so far. That claim has been vindicated repeatedly. NASA relies on these models to simulate stellar cores and gravitational dynamics. ESA uses them to interpret cosmic radiation and particle interactions. Observatories like the James Webb Space Telescope depend on atomic and nuclear physics grounded in this same framework to decode light from the early universe. The model works because it aligns with reality, not because it feels intuitive. There is one last tension worth keeping in view, because it sits at the base of everything we've just walked through. If matter can be described by the states it can take, the rules that keep those states stable and the interactions that let them influence one another, then the explanation is not hidden inside a tiny interior we can never reach. It sits in the structure of the laws themselves. Physics can write those laws with striking precision, and for what we've needed in this series, that is enough. Mass, charge, forces, and even nuclear reactions do not require secret inner parts or unseen machinery. They occur because the laws allow certain patterns to exist, to persist, and to interact in consistent ways. So the search does not have to keep moving inward. It can stop here, at the level where the rules are already doing the work. Before we end, thank you for spending your time here with me. If you'd like, feel free to share where you're listening from, or which part of this series stayed with you the most. I read those messages, and they genuinely shape how I think about what comes next. Thank you for being here.